It's great to be here in Croatia. What an awesome conference. Wow, I'm so happy to be here. Anyway, welcome. Let's see if this works.
AI, generative AI, generative AI, generative AI, AI as AI, AI. It uses AI to bring AI.
Has anyone seen this clip? I think a lot of people have seen that at this point. But what is AI? And especially for map feature creation, which is what I'm in the business of doing. What are software engineering and AI, so-called AI techniques, for creating these kinds of features? So LLMs are not the end-all, be-all of AI. There are different ways to see it, but AI is certainly not just LLMs or generative AI. Computer vision, for example, has been here this whole time. Here's another way to see it, where machine learning is a subset of AI, deep learning is a subset of machine learning, convolutional neural networks is a subset of deep learning, etc. And here's yet another way to see it, like attempts to kind of categorize different types of AI. And another one. Yeah, okay. Is it okay? Yeah, and sometimes they are presented as like false dichotomies. Like for example, it's not like unsupervised learning can't be deep learning, for example. Whereas here they're kind of put on each branch, but they, you know. All right, so what are we talking about? What are software engineering and AI techniques for HD map features? Today, I'll give some insights into what specific techniques are used for creating the kinds of features we create, which again, HD map features, and what are they for? Why HD? Why AI? That's the goal of today. ADAS stands for Advanced Driver Assistance Systems. These are the kinds of features that are needed for autonomous driving, but not only. ADAS features are very much expected or just already part of the map or GPS in modern vehicles. And they are needed for things like localization. Sometimes, as with localization, for example, features that are more important or they're more like made for machines rather than humans. Like adaptive cruise control, for example. It's something that the vehicle is doing without, like, you're not doing anything. So what's the problem, or what's my problem? For my team, we needed to move from the automatic creation of SD features, as in standard definition map features, which is what we were already doing, to creating HD map features in order to contribute to an HD map solving ADAS use cases. HD versus SD means more details, better positional accuracy, for example, from the same sources, though, by the way. It's not like, oh, before we only had like these kinds of pictures, and now we're creating HD, so now we have like better pictures. No, we have the same. We have the same. And that brings me to another problem, which is creating these very, very detailed, very, very highly accurate features at scale. So we can manually fix, improve, add to, or even manually annotate the map to make it HD. That's been done before. That's what has been done before. But that just simply doesn't scale worldwide. It's been done before in certain areas. And it's a very, very expensive thing to do. So worldwide, forget about it. And then another problem from or for, or both, my team was MLOps, or was. Deploying models into production, dealing with image compression, ability to repeat experiments, everything that has to do with machine learning operations, aka MLOps. All right, and so why should we care? Like, who cares? Recently, one of the applied scientists of my team, was training a classifier for traffic lights. This is for a specific big automotive customer. And we are creating HD traffic light boxes for this customer specifically, for traffic lights specifically, for cars. But while we were detecting and classifying traffic lights, other kinds of signals like pedestrian crossing lights, bicycle lights, etc., were also being detected because they're mixed in with our data. So we were detecting and classifying like other types of signals only to filter them out because they're not traffic lights, they're not the feature we're trying to create. And that's kind of a waste, right? So we decided that even though we don't have a customer for these other types of signals, let's say, we're going to publish them to the map anyway. And they can be really valuable signals for other downstream features, other downstream teams, whatever we don't really know. But we think that they can be used as a signal increasing the likelihood of pedestrians nearby, which can be super useful information for cars, for example. Or they can be used for localization. Any object that is localized can be used for localization, as in the car knows where in the world it is and where it is relative to other things. So, yeah, I care because maps are an integral part of our ability to plan and safely move in the world. And I think it's important that all people all around the world have access to accurate, up-to-date maps. Hi everyone, my name is Julia Wallin, and I'm the engineering manager for the road furniture and 3D tooling teams at TomTom. In road furniture, we detect and classify road furniture objects. We fuse sources, we transform them into HD map features, and we publish them to the map. That's what we do, basically. All right, so let's go through some possible solutions, some suggestions I've gotten for how we might create our features. First of all, just keep building SD features. Very few customers are asking for HD features. It's not needed. Like if we build traffic signs, which we do, customers are interested in the semantic meaning of the sign. Like, is this a stop sign? Is it a 60 miles per hour sign? What is it? They don't need all these like HD extra stuff like centimeter, positional accuracy, and blah, blah, blah. Just keep building SD map features. The problem with that, I would say, is that maybe the main problem is that we can't do it, so we should do it. And if we build HD map features, first of all, I'm pretty confident that the customers are gonna come. We can contribute to an HD map, which is extremely powerful and can be used for many things, like autonomous driving, but not only. And SD features, standard definition features, are just they're just a subset of HD features if you look at it. So if we are able to create HD map features at scale, which we are, then the SD map features that some customers might still want, it's just a derivation of those. It's just like a subset. So then, in that case, we're building, 2 for 1 in one go. Another suggestion is to manually annotate the world. Again, this is way too expensive and inefficient. We can't do that. Another suggestion is use LLMs. Hey, can you use LLMs for this? And yeah, maybe, but the data that we're processing is not natural language. It's not code, even for the most part, unless, yeah, in some cases it might be. So while there might be some use cases for LLMs, it doesn't really make sense for us to force this solution onto our problems. Just use LVMs, as large visual models. Now we're talking. And now it's getting really interesting. And large visual models, for sure, it's very, very interesting for us. And that might be the future. But for now, the models that exist are not sufficient. There are many things that we have no need for at all. This has been covered in earlier talks as well. These foundational models are very large. They cover a lot of things. And for us, it's just like a huge waste, basically. We don't need all this stuff. We just need road furniture. And neither RAG nor fine-tuning has worked so far. But that might change, though. I'd love for us to be able to use LVMs more. Like I said, we are using them in some use cases, and I'd love for it to be more of that. We can't rely on it, though. Just use SAM is another suggestion. SAM as in Meta's segment anything model. And this is also super duper interesting. And we are using SAM or SAM adjacent techniques, semantic segmentation for sure. And we may have found some even more better ways to do it, more efficient ways to segment images for our use cases. But this is a very valid suggestion, though. So what are we doing? What are we doing? We are doing object detection. So here, in this image, all of these road furniture objects need to be detected automatically. So now we're talking about computer vision tasks. Our detection model is multimodal. Oh, that's a difficult word in English. We use LiDAR scans together with images and have created a model with very high recall. High recall as in few false negatives. Few false negatives. And that's important for us to have very high recall, as in low false negatives, as in the model misses very few of the signs that are out there in the world. High recall is often at the expense of high accuracy, which is to say how correct the model is. And in many cases, when you're training a model, high accuracy is the most important thing. But for us, missing out on a sign that's really there out in the world, like let's say my detection model misses out on this, one of these signs, then that means that we have to get and process that data all over again. So that's very expensive and much more expensive than miscategorizing a sign, for example, that can be fixed in post, so to say. So our multimodal multimodal model has high accuracy, but also high recall, which is very important to us. Object detection. We are doing classification. The objects that we are detecting, these road furniture objects, has known categories that we're trying to put them in. So this is a classification problem. We don't really need to ask, I don't know, LLM or something. We have these classes. We just need to put them in the right one. We have several classifiers for different features, like traffic signs and traffic lights, for example. And we also have different classifiers depending on the source. And that's because one source might detect all kinds of lights and signals, while other sources may just detect just the traffic lights that we're interested in, for example. And in that case, a binary classifier is sufficient, or the best thing even, because then we can just ask it, hey, is this a traffic sign or not? Is it traffic sign or junk, or just something we're not interested in? But in the case that we detect all kinds of different signals, like in the case with where like pedestrian crossing lights and bicycle lights are mixed in with all the lights, then we need a multi-class classifier. So we have those as well. We train those, make those. We are doing clustering. Yes. One of our sources are so-called sensor-derived observations. So imagine that we have the observations of thousands of cars passing the same stop sign every single day. Like look around, London and Paris. We have so many traces and probably hundreds of thousands of cars just passing the same damn sign. And the sign is not going anywhere. But we don't need to use thousands of observations to create a stop sign. It's only one stop sign in the world. We're trying to model the world. And actually, that's a huge waste, right? We just need a handful of observations from recently. Let's say we make some kind of date range for us to say that, hey, it's probably a sign at location X, and we can do that with centimeter accuracy. And it's also probably a stop sign because 9 out of 10 of the observations says it's a stop sign, and the 9th is obscure that we can't really tell. So it's probably a stop sign. And if we have ground truth for that location from before, then we might just need one observation to confirm that reality hasn't changed. So we use clustering algorithms to filter the signal from the noise, or from what we don't need. There are many different algorithms, as you can see, and we need to use the right one for our use case, our problem. And we might use other techniques as well, by the way, like sampling and change detection, to only use the data that we absolutely need to create the features that we need at the quality that we need. But to process all of this data blindly, just the more the merrier, big data, yay, that's going to cost a lot and take a long time as well. We make depth maps. So monocular depth estimation is a computer vision task or process of estimating the distance of objects in a scene from a single camera viewpoint. These monocular depth maps have many applications, But for us, probably 3D reconstruction is the most important one. And this helps us to build an HD map. And then we use something called GBEM, which is a classic approach to filter LiDAR and reconstruct the bottom, meaning like the actual bottom of the road, etc. And these, like all of these things are not new. These are not techniques that came into existence over the last years. LiDAR has been used like since the 60s. I don't know. Same with creating depth maps and using GBEM. It's pretty old techniques, but compute and deep learning has definitely made it more powerful. And of course, we do MLOps. So imagine now that we have several models doing detection, we have several classifiers, etc., that we need to deploy to production and retrain and all these things. Then we need machine learning operations, aka MLOps. One of the first things that we needed to cover was how to process enormous amounts of images in an efficient way. I think everybody is aware that images takes a lot of space and videos as well. So, that's expensive and time consuming and all the things. So we have to compress these files somehow, or we'll just bankrupt the company with cloud compute. Image compression is also one of those fields which is not new, and it's a big field in computer science. I guess we can debate whether it's like, I don't know, AI or just, computer science. And it's a huge field. There's like books written up and down on image compression alone. So yeah, we need to compress the files, and we need to do it in a way that doesn't take too much away from the quality of the images, because then they are useless for our computer vision tasks. And also, importantly, they are useless for like human-in-the-loop type of processes, where maybe we take a sample of images and send them to people and ask like, hey, the model says this, is that correct? We need to be able to view these images. So that's like the first thing to tackle. That's just one aspect of MLOps for us. But there's so much more to MLOps, right? Building and testing, packaging and deploying, monitoring, etc. But these were some AI techniques we use to create HD map features, and that allows us to do it at scale. So what's next? For us in road furniture, we have a pretty long backlog of 3D objects that we want to detect and classify and publish to the map. Guardrails, bus stops, poles, benches, all kinds of objects. The list is finite, though, but we have work to do for the foreseeable future for sure. And in terms of use cases, we don't know yet. Like with the example with the traffic lights, we don't know like how someone might be able to use pedestrian light crossings, because we haven't really made them before, and there's probably a bunch of different use cases. From what I know right now, the list of products and map features then that can use our objects as signals is pretty long. And that's it. That's what I had. And with that, I hope you've been convinced that AI is so much more than generative AI and LLMs. my team has so much to do and will use LLMs for a very tiny portion of it, if at all. So thank you. I'll be around, connect with me and LinkedIn and say hi. And thank you all so much for listening.